Welcome to the world of the HADI S's Aetherion Discus, a revolutionary leap in aerospace engineering designed and developed by Colonel James Edward Hartman, Northwest Indiana. This video will guide you through the integrated systems, advanced materials, and multi-environment capabilities of this lenticular craft. Unlike traditional vehicles, the Aetherion Discus is not just a flying saucer. It's a unified, field-managed platform where every subsystem works in harmony. From its transparent metashell to its distributed propulsion and predictive sensors, every detail is designed for seamless operation across air, sea, land, and even the upper atmosphere. Let's embark on a journey through its origins, design, philosophy, and the science that powers its extraordinary performance. The shell's performance is quantified by key equations. The stress relation is given by $sigma equals frac F a dollar, where force is distributed over area. The effective modulus, $E F equals E, 0,1 plus chi, n plus chi, F dollar, accounts for nano and fiber reinforcement. The wave transport mesh follows the dispersion relation omega 2 equals omega 0, 2 plus C S 2 K $2, while the auxetic core's density adapts as rho F equals rho 0,1, beta frac, omega 2, omega R2, $. These formulas ensure the shell's strength, adaptability, and wave-carrying capacity. The propulsion system's performance is governed by several equations. The waveguide propulsion ring's resonance is omega n equals frac n pi c F L $, where $n is the mode number, $C F $ is effective wave speed, and $L is ring length. Thrust is approximated as $T WGPR, approx, kappa, frac, P, ring, C, F, $. The steering array's net thrust is $T net equals sum I equals 1 N T I $, with each emitter contributing a time-varying vector. These relationships enable distributed, responsive propulsion and steering. The energy system's operation is described by key formulas. Stored energy is $E equals frac 1 2 C, FV $2, where $C F $ is effective capacitance and $V $ is voltage. Magnetic energy density is U, B equals frac B 2 2 mu 0 $, with $B $ as magnetic field and mu 0 $ as permeability. The total system energy is E, system equals E, Q plus E, B plus E, H $, and energy balance is frac DE. dt equals P, in, P, prop, P, control, P, loss, $. These equations ensure the craft's power is always optimized for current demands. The sensor system's operation is mathematically rigorous. Sampling follows $F S GE2F G $, ensuring accurate data collection. The predictive command law is $A CMD equals A ref K PG pred G mes $, where $A CMD is the command acceleration, $A ref is the reference, $K P is a gain, and $G pred and $G mes are predicted and measured gradients. These equations enable the craft to adjust its behavior in real time, maintaining optimal stability. The Aetherion Discus is designed for 5 distinct operating modes: sea, lake, land, sky, and upper atmosphere. Each mode optimizes the craft's systems for the specific environment. For example, sea mode emphasizes hydrodynamic smoothing and acoustic damping, while sky mode focuses on drag suppression and omnidirectional flight. The mode selector ensures seamless transitions, allowing the same vehicle body to excel across multiple domains. In C mode, the Aetherion Discus shifts its system weighting to prioritize hydrodynamic smoothing and acoustic stabilization. The lower propulsion ring increases stabilization, while acoustic systems dampen waves and distributed emitters control hover elevation. Sensor arrays monitor water density, turbulence, and surface topology, ensuring smooth and efficient movement through aquatic environments. Lake mode is tailored for surface stability and low-speed maneuvering. The craft uses its buoyant support systems to maintain a steady position, even in variable conditions. The sensor grid provides constant feedback, allowing for gentle, precise adjustments. This mode is ideal for operations that require minimal disturbance to the water surface and high positional accuracy. On land, the Aetherion Discus transitions to hover support and terrain-aware movement. The craft's steering and acoustic layers work together to provide zero-contact landing and active balancing. Sensors map the terrain in real time, allowing the vehicle to follow contours and avoid obstacles without ever touching the ground. This capability is crucial for delicate or hazardous environments. In Sky mode, the craft's systems focus on drag suppression, lift balancing, and omnidirectional flight. The shell's aerodynamic design reduces resistance, while the propulsion and steering arrays provide agile, multi-axis control. The sensor grid predicts turbulence and density changes, allowing the craft to adapt instantly to atmospheric conditions. This mode enables high-speed, stable flight in complex airspace. When operating in the upper atmosphere or near space, the Aetherion Discus emphasizes field stability, thermal management, and low-density control. Traditional aerodynamic surfaces become less effective, so the craft relies on its field-based propulsion and distributed steering. The sensor grid shifts focus to magnetic field mapping, radiation monitoring, and inertial tracking, ensuring safe and efficient operation in extreme conditions. The engineering diagrams of the Aetherion Discus use colored field lines to illustrate system interactions. Cyan arcs represent electromagnetic momentum flow, white rings show acoustic pressure nodes, gold loops indicate energy circulation, green rays mark sensor scanning, blue dashed curves highlight inertial shear gradients, and purple traces reveal coupling pathways. These visual cues help explain how the craft's subsystems interlock to create a responsive, adaptive platform. To visualize the field interactions, imagine a cutaway diagram of the craft. Electromagnetic arcs, acoustic rings, energy loops, sensor rays, inertial gradients, and coupling traces are all shown in distinct colors. Each field supports a specific function. Electromagnetic transport guides, waves, acoustic nodes, stabilize lift, sensor vectors, enable prediction, energy loops, power active systems, and inertial zones reduce maneuver burden. This integrated field logic is what sets the Aetherion Discus apart. Whether in air, sea, land, or upper atmosphere, the Aetherion Discus operates as a single, unified system. In air, the shell reduces drag, the propulsion ring generates momentum, the steering array manages fine movement, and the sensor grid predicts turbulence. In sea, the craft emphasizes hydrodynamic smoothing and acoustic stabilization. On land, it provides hover support and terrain-aware movement. In the upper atmosphere, it focuses on field stability and thermal management. The core system remains unchanged, only the field weighting adapts. Colonel Hartman's redesign introduced several key improvements: a transparent layered shell, clearer subsystem naming, higher density steering, toroidal energy routing, predictive sensing, mode-based environment control, exploded view documentation, and technical math overlays. These upgrades make the Aetherion Discus not only more advanced, but also easier to understand and operate as a complete system. The Aetherion Discus is underpinned by a suite of mathematical models. These include stress and modulus relations for the shell, resonance and thrust equations for propulsion, energy storage and balance formulas, sensor sampling and prediction laws, and mode selection logic. Together, these equations ensure every subsystem operates at peak efficiency and adapts to changing conditions in real time. The Aetherion Discus is not a collection of isolated technologies. Instead, it's a continuous, integrated system where structure, waves, energy, sensing, environment, and steering all operate as one. This synthesis is what allows the craft to function seamlessly across air, sea, and space, adapting instantly to new challenges and environments. Earlier, flying disc concepts often failed because they treated each subsystem as independent. The Aetherion Discus, by contrast, is built on the principle of distributed integration. This approach draws from the lessons of past designs, combining electromagnetic lift, acoustic stabilization, and field propulsion into a single, cooperative system. The result is a craft that is both innovative and grounded in scientific tradition. A key feature of the Aetherion Discus is its continuous subsystem interaction mapping. Predictive environmental sensing, integrated field overlays, and dynamic energy balancing ensure that every part of the craft communicates and adapts in real time. This mapping is visualized in technical diagrams, showing how each subsystem supports and enhances the others. To make the complex architecture of the Aetherion Discus understandable, exploded view diagrams are used. These visuals separate each subsystem, shell, propulsion, energy, sensors, and control while showing how they fit together in the complete craft. This documentation approach makes it easier for engineers and researchers to grasp the full system logic. The core concept behind the Aetherion Discus is the field-coupled vehicle. Unlike traditional craft, where propulsion, sensing, and control are separate, here every subsystem is linked by shared field effects. This means the hull itself participates in propulsion, sensing, navigation, and stabilization, creating a truly unified technological platform. The HADI S's Aetherion Discus stands as a testament to modern aerospace integration. It preserves the visionary ideas of its conceptual forebears while adding original structure, subsystem clarity, and technical coherence. As a unified, field-managed vehicle, it represents the future of multi-environment craft, where every layer, every field, and every subsystem works together as one. This is not just a new vehicle, it's a new way of thinking about flight, transport, and adaptation.